Let's have a look now at the second derivative and what it tells us about the function. You're probably going to find big similarities between what I'm going to say now and what I just said about the first derivative analysis, and that's because the method is pretty much the same. The only difference is that we're going to be dealing with we're going to be analyzing in the same way the second derivative, and therefore the conclusions we're going to reach are going to be a little bit different, the conclusions about the graph. Okay, so first of all, something that you're probably very familiar with. Well, if the second derivative is positive, what does that mean? It means that the slope of a curve is increasing. So what does that mean? The slope of the curve may be starting low or very big negative, and then it gets flatter and flatter. So that means closer and closer to zero. So then it reaches zero maybe, and then it keeps going up into the positive. So the slope is going up, and we express that by saying that the concavity is up. Okay, so it looks like a cup or a bowl, right, or a valley. On the other hand, if the second derivative is negative, that means that the slope of the function, the first derivative, is decreasing, is getting lower. And therefore, it means that your curve is starting with maybe a big positive slope, and then the slope is getting smaller and smaller, and then it's becoming pretty flat, and that's going to the negative and more negative. And so in this case, we say that the concavity is down, and this thing will look like an umbrella or an upside down cup, whichever you prefer. Okay, so these are things that I assume are still should be very familiar to you. If not, just think about them and review them as you need. Let me now clarify something about inflection points, okay? Because in my experience, sometimes students have some inaccurate ideas of what inflection points are, and so I want to make sure that that you are clear on that. So, in other words, in order for us to have an inflection point, first of all, we have to have a point. So, and not only that, but we're going to expect and require that the function be continuous there. So it cannot be an isolated point outside of the graph of the function or some really strange point. It has to be a point where the function is nice and continuous. And the second derivative has to change sign as it goes through this particular point. So in other words, it may come from being concave up, may change from being concave up to concave down, or may change from being concave down to concave up, but the concavity has to change. So the fact that the second derivative itself is zero or undefined is not enough for an inflection point. We need to have a situation where the concavity actually changes. So for instance, if the curve looks like this, that might be an inflection point because the concavity is changing from being up to being down. Okay, so as we look for these inflection points, we have to make sure we have a point, that the function is continuous there are no jumps, no other strange things, no asymptotes, for instance, and that the concavity is changing as we move across that particular value, that particular point. So this leads us to using the second derivative and to analyze it completely to get the concavity pattern of a function. And the procedure here is very similar to the procedure we used for the first derivative. So what we're going to do is first of all find the cut points of f double prime of x. So those are the values of x for which the second derivative becomes 0 or becomes undefined. Then we're going to use those to solve the inequality f double prime greater than 0. This will tell us where the function is concave up and where it is concave down. By the way, notice that both in the first and second derivative analysis, we had to solve an inequality, and some of you I know are still a little bit rusty on that. So I definitely encourage you to review all the information and the material that you have on inequalities so that you can do that fairly quickly, efficiently, and accurately. So once we have solved this inequality, and we know where the concavity of the function is up and down, then we can identify each cut point as an inflection point if everything is fine, continuity, change of concavity, and so on, or if it's something else based on some other information that we have. And so as you see, the strategy is exactly the same as the first derivative, only the conclusion is about concavity. Now, there is also a second derivative test, just like there is a first derivative test. But guess what? This test has nothing to do with concavities or inflection points. And again, you're going to find this fairly commonly in basic traditional standard textbooks. Okay, but again, this is just a test to classify the critical points. These are the ones for the first derivative, remember? So these are just this is just a test that tells us whether critical value is a maximum or a minimum. It tells tells us that if you have a critical value where the concavity is up, then we're talking about the minimum. Of course, if the concavity is up, we're dealing with a cup, so we're looking at the bottom of the trough. On the other hand, if you have a concavity down, then we're talking about a maximum. Now, this is a good test, nothing wrong with it, except that it's inefficient. Okay? You have to go all the way down to the second derivative to find out something about what is really a first derivative feature. So even though there's nothing wrong with it, and if you're used to it and if you like using it, by all means feel free to do so. But remember, the best way to know something about the critical values, the critical points, is to do a full first derivative analysis of the function. Okay? So always perform a full first derivative before moving on to the second derivative. And if you want to be efficient in your analysis, make sure that you reserve the second derivative analysis for finding concavities and for finding inflection points. Leave everything else about the up-down pattern, critical values, max, min to the first derivative analysis. You may want to use the second derivative test to confirm what you have found before, but again, you have to be careful. Oh, and by the way, the second derivative test doesn't always work, while the first derivative analysis always tells us if a critical value is a max or min or something else. So have fun with that. We'll spend a couple of times going through these ideas with different functions, and I certainly encourage you to try your hand on as many functions as possible. There is a handout on Blackboard. There's a list of functions, and pretty much all my major test questions will be functions taken from that list with some minor modifications. So practice on those as much as possible and become really proficient in graphing functions. And of course, when we're talking about graphing, the issue of calculator comes up. Use it as usual as a help, as an assistant, not as a crutch, and don't trust it all the time.